Hello. So in this video, we're going to look at Laplace's equation inside a circular disk. So in the last video, we looked at same equation, Laplace's equation for a rectangle. Okay, but now what we're going to do is change the geometry a bit. And so kind of the picture to keep in mind is, right, so here we have our disk, okay? And the region that we're interested in is the interior of the disk. Okay. And we're given some boundary information. And so we're told kind of the temperature at the boundary of the disk is maybe some function f, where I've drawn in purple the profile of f, and I've also drawn straight lines kind of from the circle straight up to the function f. So this is our initial condition, okay, or boundary condition, what have you. And the PDE that we're interested in is, so nabla squared u is equal to 0. In polar coordinates, nabla squared takes this form, okay? So we're seeking functions u such that this thing is 0, as well as the value of u at r equals a, which for our geometry corresponds to kind of circle. The value of u on that boundary circle is equal to this given function f of theta. Okay. So that's the problem that we're going to be looking at right now. Okay, so one thing to keep in mind is that, so here, right, in a sense, we've only given one boundary condition, okay? So we specify the value of u at r equals a, but in a sense, there are 3 other boundary pieces we have to worry about, okay? And so that's illustrated kind of here. And so, right, keep in mind that, right, technically the region that we care about is 0 is less than or equal to r, okay? So non-negative radius cannot be larger than a. And then the angles that kind of we care about, or that we can plug into our function, the possible angles are going to be between negative pi and pi. Okay. So if you look at, right, r between 0 and a, and theta between negative pi and pi, if you draw that, you're going to get something like this rectangle, right? So r equals 0 is this line, r equals a is this line, theta equals negative pi is this line, theta equals pi is that line. Okay. So this is kind of our parameter space. But then when we map from these parameters, r and theta, into Euclidean coordinates and really plot kind of the region that we care about, we're going to end up with, right, a circular disk. Okay. And so the colors here for these lines are meant to show you kind of, right, where these, we'll say, coordinate lines get mapped to, right? So this pink line, for example, right here, if you map from, right, polar to Euclidean, this pink line here is going to get mapped to this pink circle here, okay? Likewise, this purple line right there gets mapped to that purple line. Okay? And then this dark blue line right here, right? This dark blue line corresponds to r equals 0. So this dark blue line gets sent to this point right here, okay? You can also ask, well, where do the lines theta equals pi and theta equals minus pi, where do those get sent? Okay. So generally what we do is we say, well, so right here, this black line right here, this is theta equals 0, right? And so then this, let's say, brown line right here, so as you approach from up there, that's theta equals pi. As you approach from below, you're approaching theta equals negative pi. Okay. And so then this line segment right? What we're doing is we're effectively gluing it to this line segment. Okay. And then where does this line segment get mapped to? Well, it gets mapped right there. So if when theta is 0, that's this line segment right there. That gets mapped to that. Okay. So in practice, right, we're solving an equation on this geometry, okay, on a circular disk. Is the right thing? Okay, let me clarify. So this is a picture that we have in mind for our solution, kind of where the geometry actually comes into play. But in reality, what we're doing is we're solving a different PDE on a square or a rectangle. Okay, so kind of the computations and everything we do, they'll feel this geometry, but then the output will kind of see this geometry. So for the present discussion, kind of how does that play in? Well, if we look back at our boundary conditions, we're saying u of a comma theta is equal to f of theta. Here we've only specified boundary conditions for when r is equal to a. Okay. So in a sense, what we're doing is we're only specifying boundary conditions right here. And so if we actually want to compute solutions and work with everything, we also need to specify boundary conditions for here, here, and here. Okay. And so kind of written out, well, what is u of 0 comma theta? That's this line segment right there. We need to impose some boundary condition here. Keep in mind that in the end, all the points along this line segment get mapped to a single point. Okay, so that's something that we'll have to keep in mind, but regardless, we do have to specify something for r equals 0. Likewise, we're going to have to specify something for theta equals pi and theta equals minus pi. Okay. Kind of the resulting solution, we'd like to think that it's continuous as you pass over, say, you go from theta equals pi, and then you keep walking along to kind of the theta's negative region. You would like your solution to be continuous. Okay. And then moreover, we'd also like it to be kind of the derivatives to match up as well, at least the first derivatives. Okay. So in a sense, the solution is both continuous and there's not like a kink or anything. It's continuous and smooth, say, or at least differentiable. And so that boundary condition we'll write like this. For every r, right, what is the temperature at theta equals minus pi? Well, since we're gluing kind of that line segment minus pi to pi, we would like the function u to be continuous kind of across that line segment. And so in practice, what we do is we say, well, u of r negative pi is equal to u of r comma pi. And then the condition on the derivatives kind of being continuous, or the function being differentiable across that kind of boundary piece, plays in here. Okay. So this establishes that our function is continuous across kind of that theta boundary piece, but we still need to do something about our solution function at r equals 0. Okay, and so the condition that we'll actually impose will be that whatever the value is at 0, that is finite. And so you might think, well, I mean, that's obvious, right? If you have kind of an equilibrium heat distribution, or in general, anything physical, right, your solution is not going to blow up. You're not going to get some sort of singularity, which, intuition says, sure, right. So, turns out that that's what we'll impose. In practice, when we actually go to compute solutions, this condition will show up to be rather, say, indispensable. Okay, and we'll see that a little more explicitly. But you could say, well, that's obvious. We don't want our solution to blow up, but this is something that we have to impose, like pretty directly for this problem to have, let's say, solutions that we would expect to see physically. Okay. Okay, so in any case, this is a new PDE that we're working with, right? Recall before we had just written these two pieces. Now we're explicitly also writing out these pieces. Okay. But this is a PDE that we're gonna play around with for now. Okay, so we're gonna use our tried and true technique of separation of variables. So we're going to separate our solution function u of r comma theta into a piece that just depends on theta and a piece that just depends on r, the radius. So if we make the separation, then what we end up with, right, plugging this in to this PDE for u right there and u right there, right, we're going to get this expression, right? So these r derivatives only affect phi, or sorry, these r derivatives only affect g and not phi, because phi is a function of theta. Likewise, these theta derivatives only affect phi and not g. Okay. And I think I'm missing a k. Nope, we're good to go. So sometimes, I guess there's a k right there. Assume k is 1. If you want to incorporate a k, you can follow this, just incorporate that constant, but I guess for now, we won't worry about it. But okay, in any case. So plug in our product solution. Okay, we're going to get this. Isolate the functions of r and theta on each side. What do we end up with? Well, so all of this is equal to 0. Move all the theta pieces to one side, keep the r pieces on the other side. We're going to end up with this expression, okay? And the observation is, well, here, right, here, things only depend on r. Okay? Over here, things only depend on theta. So kind of as before, both sides are equal to some constant, which we'll write as lambda. Okay, so we'll keep lambda positive here. And the thinking is, well, the boundary conditions that we imposed on phi, right, coming from theta, those are ones that we've seen before in the case of like a thin circular ring and heat conduction on a thin circular ring. Okay. And so in that case, right, what we relied on was the PDE minus lambda phi, something like that, right? And what that gave us then was kind of a nice representation for lambda, as well as these oscillatory solutions, in this case, a sum of sine and cosines. Okay. And so, right, because we've seen these boundary conditions before, and they gave rise to sines and cosines, we're going to keep kind of this minus sign with the phi pieces. And so to keep that minus sign with the phi pieces, we need a positive lambda there. That's the choice of sign. You could go through this whole analysis with writing a minus lambda instead. Totally fine. You'll get the same answer. Just here, we're using it so that it's easy to match with things that we've done before. Okay. So then the resulting ODEs look like this. So this is the phi piece, right? With kind of the continuity and smoothness condition at the theta boundary. And then the other piece is this expression. So keep in mind that this ODE is an eigenvalue problem, and it gives us enough information to figure out both what phi is, as well as what lambda is. So once we've solved this for both phi and lambda, we can take that lambda and plug it in right there and then solve for G. Okay, and so that's going to be our strategy. Okay, and so without going through the full analysis for phi, right, it's contained in an earlier video. The observation is that then, well, the eigenvalues that we get for this problem are going to be, again, n pi over L quantity squared. What is the length of kind of our material in this case, or our region? Well, we're starting at minus pi, and we're going up to pi. Let's see. No, so I take that back. So the situation that we worked with before, if you recall, we were working with d squared phi over d theta squared is minus lambda phi. And then u of minus, or u of r comma minus L is equal to u of r comma L, etc. And what we ended up with was lambda was n pi over L squared. There we go. So in this case, what we're doing is, well, what is this length L? Kind of half the length of the interval. In this case, L is exactly pi. Okay, so plugging in pi here, plugging in pi there, we get n pi over pi squared, which simplifies just to n squared. So our eigenvalues are exactly n squared for this specific problem. And our eigenfunctions are going to be a linear combination of sine and cosine, which again come from both of these boundary conditions. Okay, so it's not just cosine, it's not just sine, it's both of them. Okay, but this is all analysis that's been done before for the thin heat insulation on a thin ring. Okay, so now we know what lambda is. And so coming back up here, we can plug in lambda here and then solve this piece. Okay. So let's see what that gives us. So here's that same ODE with lambda plugged in. What we're going to do is multiply through by G. So multiply G on both sides. We get the Gn squared. And what we're going to do as well is distribute this DDR, right, into this product. So we're going to use a product rule. So we have R times DDR applied to R times DGDR. Okay, that's going to give us R DGDR because DDR of R is 1. Okay, so this is one of the pieces. The other piece we're going to get from R times DDR applied to DGDR, all of that times R. And that's going to give us this piece. Okay. And then we're going to move this n squared times G over to the other side to end up with this. Okay. And so then the condition is, well, right, if we go back up here, we want, where was it? We want the value of our function at 0, at r equals 0 to be finite. Okay. So the piece of our solution function that depends on r, that was G. Okay. So what that tells us then is, well, what kind of the boundary conditions that we're given, how does that play into the separated variable situation? Well, in this case, we need G of 0 to be finite. I guess you could write it out, right? U of 0 comma theta finite means that G of 0 times phi of theta, that's finite. Okay, and so that has to hold true for every possible theta, so every possible phi of theta, which forces G is 0 to be finite, because we know what phi looks like. Okay. Okay, so this is not necessarily a standard ODE. Well, it's a less standard ODE, particularly because there aren't constant coefficients, right? So in this case, what we're going to do is we're going to say, well, there are a lot of R's involved, right? And kind of the R's match the order of the derivatives that we're applying. Okay. So what we're going to do is we're going to look for solutions of this form, right? Similar to kind of the constant coefficient case, we say, well, assume that the solution function is of the form e to the rx. What is r? Okay. Here, what we're going to do is we're going to say, well, assume that the functions are of the form r to the p. What must p be? Okay. So we have a second derivative in g, a first derivative in g. So what we're going to do then is compute these derivatives. So dg dr, right? Carry the exponent down and then subtract 1. D squared g dr squared, same game. Bring this exponent down and then subtract 1. Okay. And so now what we're going to do is just plug each of these pieces into the ODE up here. Okay. So what does that give us? So here's the ODE. Plugging in for what we computed this, and then what we assume this to be, we get this expression, right? So this r squared carries down. This dg dr is exactly that, etc. Multiply this r squared by the rp minus 2. Multiply this r by the rp minus 1. And then I believe collect terms, we're going to end up with this, right? So this with this gives us an r to the p. This with this gives us an r to the p. This is an r to the p. Factor all of these out. We're left with this. Okay. And so this has to hold true for every possible r. And so the conclusion is, well, this thing right here has to be 0. Okay. Which, expanding, we get something like this. These p's are going to cancel. And so we're left with p squared minus n squared is equal to 0. Or in other words, p is going to be plus or minus n. Okay. So for a given lambda, right? Recall lambda was equal to n squared. Okay, so right, lambda depends on n. For a given lambda, we figured out what the form of g has to be. It has to be r to the n. Well, it has to be r to the n, a linear combination of positive n and minus n. Okay, so it's going to be some linear combination like this. But again, this is one of our building blocks. Okay. Keep in mind, though, that this is for n less than or equal to 0. I guess you could kind of bring in n equals 0 and try to make that work with everything else. But for this lecture, I'm going to treat these cases differently. So we're just going to say all of this, we're most comfortable with n different to 0. Okay. And then what we're going to do is ask, well, what happens when n is equal to 0? Maybe another way to kind of intuit this is, right, so p here is plus or minus n. Okay, so when n is equal to 0, g here is equal to 1, or a constant. And so this expression for g is false, right? Because if you have a constant and then you take its derivative, you're going to get 0, which I guess here this holds. But then, okay, take a second derivative, right? Second derivative of 0 should be 0. So I guess this still holds. we're going to treat it differently, or we're going to kind of look at it as a special case. Anyway, okay. But before then, right, so notice that we have a C1 and a C2, okay? And so the question we're going to ask right now is, well, can C2 be non-zero? Okay. And so kind of the motivation is also going to play into the answer. So recall that we impose this boundary condition, right? G of 0 is finite. Okay. So if C2 is non-zero and n is non-zero, right? Question is, what is going to happen as r goes to 0, right? Because r equals 0, that's one of the points in our domain, one of the points that we care about. And so we want to make sure that this piece satisfies this condition for all the points that we care about. So what's going to happen? Well, take the limit as r goes to 0. What's going to happen is this term right here is going to go to 0, right? Because we just have an r to the n. That's no problem. But this term right here, this is going to go to infinity. So if C2 is non-zero, then our solution G of r is going to blow up as r goes to 0, which is exactly the condition that we said we don't want to happen. Okay. So in conclusion, we say, well, the coefficient for r to the negative n, that has to be 0. And so then, yeah, so this is 0. So it tells us that our solution for G is just this piece right here. Okay. So if we take this piece and then multiply it by the piece that we found for phi, which is this piece for each n, what we're going to end up with is kind of a product solution that looks like this, right? So some arbitrary constant a sub n, which we'll be able to compute later, times the radial piece, G of r, times the cosine piece, okay, together with some constant b sub n times the radial piece r to the n times the sine function. Okay. Okay, and so here, keep in mind that, right, these radial pieces, these are, right, that G of r, and then those other pieces are phi of theta. And so in some sense, this a sub n and this b sub n, these were what we had written up here as C1 and C2. Okay, but the point is we've computed what these basic product building blocks are. Okay. Okay, and so then the other question is, well, what about lambda equals n squared equals 0? The case that I've been trying to avoid and try to treat as a special case. So here, right, for our solution function, the radial piece G of r, right, when n equals to 0, this is the solution we'd get, right? And so this fits in with the framework from before. But keep in mind, though, that we have another possibility when n is equal to 0 for the radial piece. Okay. So if we go back to the ODE, and so here I've included a k, but set k equal to 1. Technically, right, so this was the lambda, which was n squared. So if n is equal to 0, then we have this piece right here is equal to 0. Multiply through by this to get rid of it. We're left with ddr of r dgdr is equal to 0. Okay. Integrate once in r, you're going to get that, right? So integrate dr, integrate dr. You're going to get r dgdr is equal to some constant right there. Move things around, you're going to get dgdr is equal to c1 over r. And then integrate once more, you're going to get g of r is equal to c1 times ln of r, right? Because integral of 1 over r is equal to ln of r plus some other constant. So technically, right, so here was our constant piece, and then here was our kind of the other linearly independent solution we found. But keep in mind that we want g to not blow up as r goes to 0. Okay. Well, so if we write out what this is, right? So I'll say as r goes to 0, c2, this is just a constant, right? Doesn't depend on r. But ln of r, this is going to go to minus infinity. Okay. So if c1 is non-zero, then g of r is going to blow up as r goes to 0, which we want to avoid. So that forces c1 to be 0. So the only possibility for g when n is equal to 0 is the constant solution, which we saw before. Okay, so then the general solution we can write in this way, right? So we have the constant piece, right? The c2, which also came from kind of this cosine series. Well, you have this constant plus all of the cosine terms, summing up over all possible eigenvalue n squared, plus all of these sine terms. Okay. And so this is going to be our general solution for Laplace's equation on kind of a circular disk. Okay. So almost all well and good, right? Keep in mind the boundary conditions we've used were g of 0 is finite, okay, as well as the boundary conditions on phi. Okay. But in total we had, where was it? In total we had 4 boundary conditions. Okay, so the last boundary condition we have to deal with is the value of u at r equals a, and that's some prescribed function of beta. Right, so one way to phrase this is, well, right, here's our general solution. Can we determine these constants? And the answer is yes, using our 4th boundary condition. Okay, so if we want to match this boundary condition where u of a comma theta is equal to f of theta, what we're going to do is we'll just plug in r is equal to a, right? So I can scroll back up here. So this is going to be a to the n right there. And then all of this is going to be f of theta. And that's exactly what's written right here. Okay, plug in r equals a. And then the condition is, well, f of theta has to be written in this way. Okay, that's the condition on our boundary condition f of theta. And so from all of this, can we figure out what a sub n and b sub n are? And it turns out the answer is yes, we can. By the same trick we've been using before, where we multiply both sides, say this by, for example, sine of n theta, and then this side by sine of n theta, integrate with respect to theta from minus pi to pi, and then use certain properties of the sine integrals to isolate a sub n and b sub n. Okay. So what does that look like? Well, a sub 0 is just going to be 1 over 2 pi, integral f of theta. A to the n times a sub n is going to be 1 over pi integral of f of theta cosine of n theta. And so if we want to figure out what a sub n is, well, here we just need to divide by a to the n. And then finally, for the sine coefficients, same thing, we have a to the n times b sub n. That's going to be 1 over pi times the integral of f theta sine of n theta, d theta. But the point is that, right, we know how to match these coefficients to the given kind of boundary condition. Okay. And so that means we can figure out what a sub 0, a sub n, and b sub n are, which means we can figure out what this general series solution is, which means we have a construction for solutions to this PDE. And that was the whole point of this, this lecture. Yeah.